Welcome to This Explainer. Okay, let's get right into it. Strap in, because today we're going on a high-energy, step-by-step deep dive into mastering dry friction. Whether you're studying mechanical, civil, or industrial engineering, this one is absolutely for you. Look, I know how incredibly daunting engineering statics can seem, especially when those final exams are looming right around the corner. But today, we're going to break down these concepts so clearly that you'll literally be visualizing free body diagrams and 3D surface interactions in your sleep.
Our agenda today is packed. We've got 1. Real-world applications, 2. The laws of dry friction, 3. The 4 contact situations, and 4. Step-by-step problem solving.
Starting with Section 1, Real-World Industrial Maintenance. Let's see how friction is somehow an engineer's absolute worst enemy while also being their very best friend.
Just picture the massive amounts of kinetic energy flowing through complex 3D mechanical systems. In automotive and industrial maintenance, we deliberately engineer high-friction materials for things like drive belts and disc brakes. I mean, we absolutely need them to grip aggressively to transfer power or to safely stop thousands of pounds of moving steel, right? But then, conversely, think about engine pistons or journal bearings. For those, we demand exceptionally low friction. If those components catch even a little bit, the resulting heat failure is just catastrophic. So engineering is really all about perfectly controlling this delicate balance.
Moving to Section 2, the laws of dry friction. Now that we understand the real-world stakes for modern machinery, let's break down the rules of how this actually works. So the most crucial point to grasp right away is that not all friction is calculated the same way. We essentially live in two different worlds here. There's fluid friction, which involves lubricants like the oil protecting those engine pistons we just talked about. And then there's dry friction. This explainer is going to focus purely on dry or Coulomb friction between non-lubricated surfaces, because this right here is the absolute foundation of structural stability and statics.
All right, imagine you're pushing a really heavy wooden block. As you increase your applied horizontal push, which we'll call force P, the static friction force, F, pushes back equally. The friction literally rises perfectly in sync with your push. It stays in a state of complete equilibrium until it hits a breaking point. We call this peak impending motion. The very millisecond the block finally gives way and snaps into a slide, the friction suddenly drops down to a steady, slightly lower resistance, which is known as kinetic friction.
And the actual resistance you feel, that brilliantly illustrates how deeply friction depends on the specific materials that are making contact. The coefficient of static friction varies wildly. For instance, you have slippery metal on metal with a coefficient sitting as low as 0.15 all the way up to the highly aggressive locking grip of rubber on concrete at 0.9. This coefficient is really just a mathematical way of representing how rough and physically intertwined two microscopic surfaces are.
Okay, quick exam tip here to wrap up this section. Definitely lock this into your memory. The total friction force is directly proportional to the normal force pressing the surfaces together, and it depends heavily on those surface conditions we just covered. But here's the trick question professors absolutely love to throw at you. Friction is completely independent of the contact area. It literally does not care if a block is lying flat on its wide side or standing straight up on a narrow edge. As long as the normal force and the materials are identical, the friction force remains exactly the same.
Section 3, the 4 contact situations. Let's visualize the 4 distinct physical states a rigid body can experience when resting on a surface.
First up, we have a state of zero friction. This happens when the applied forces are perfectly vertical. Remember, friction only exists to oppose lateral movement. Compared to that, our second state is no motion. A lateral push is being applied, yes, but it is completely absorbed and neutralized by the static friction force. The block is perfectly stable. Let's test your statics intuition with a quick subtopic quiz. If you keep pushing harder and harder, but the block stubbornly stays put, what exactly is mathematically happening to that friction vector? Does it just stay the same? Well, the answer is that the friction force physically grows to perfectly match your push. It builds and builds until it reaches its absolute maximum static capacity, Fm. This is state 3, right at the fragile tipping point of impending motion. If you so much as breathe on it, it moves. And once it finally does move, we enter state 4, giving way to that lower kinetic friction as the block begins sliding across the surface.
Section 4. Step-by-step problem solving. This is the fun part, where we bring the physics and the math together to totally crush a real exam problem.
Here is your foolproof 3-step blueprint for solving any equilibrium problem involving dry friction. Step 1. Isolate the object and draw an accurate free body diagram, making absolutely sure your friction vector directly opposes the intended motion. Step 2. Define your knowns and figure out exactly what unknowns you need to solve for. And Step 3. Deploy your sum of forces equations in the x and y directions.
Let's put this into a real-world industrial context. Picture this scenario. We have a heavy mechanical block sitting on a 25-degree steel incline. It's under multiple directional loads. There's a horizontal 750 Newton push and a vertical downward crushing force of 1.2 kilonewtons. We are given a static coefficient of 0.35. Our job as engineers is to determine mathematically, will this block stay safely at rest or is it going to slide down and cause a failure?
But wait, before we start crunching those numbers, here is another quick quiz to help you avoid the most common trap engineering students fall into. Should you immediately use the classic formula where friction equals the static coefficient times the normal force?
The answer is unequivocally no. Do not do this. You must assume the system is in equilibrium first and calculate the actual real-world friction required to hold it there. You can only blindly use that formula if the problem explicitly tells you the block is on the verge of sliding. Right now, we have no idea if it's at its breaking point, so we have to do the math to find out. Let's walk through these calculations step by step. By setting up our free body diagram, we can actually tilt our x and y axes to seamlessly match the 25-degree incline, which makes the math so much cleaner. We then resolve our 1.2 kilonewton and 750 newton forces into their angled components using our basic sine and cosine trig functions. When we sum the forces along the y-axis to 0, we calculate a massive normal force pushing out from the surface, coming in at 1404.5 newtons. Next, summing the forces along the x-axis to 0, we find that to keep this block perfectly still, we only require a friction force of 172.6 newtons holding it up the ramp.
But is that 172.6 newtons actually available to us? Let's check the maximum capacity. We multiply our normal force of 1404.5 by our static coefficient of 0.35. That yields an absolute maximum available friction, our M, of 491.6 newtons. Because our required friction is only about 173 newtons, it is well below that 491 newton breaking point. We are solidly in the safe zone, proving conclusively that the block is in stable equilibrium and will not slide.
To wrap up this section, remember these core takeaways to ensure success on your finals. Number 1. Always drop perfectly accurate free body diagrams with friction directly opposing the slide. Number 2. Never jump to calculating maximum friction unless you are specifically checking for a failure point or impending motion is explicitly stated. And number 3. Practice resolving those multi-axis forces carefully with your trig functions. We've covered a ton of ground in this explainer today, from heavy industrial mechanics right down to precise step-by-step statics calculations. But I want to leave you with this final thought. Now that you've mastered isolated 2D static friction, how do you think these microscopic surface interactions scale up when you have hundreds of massive 3D rotating components interacting simultaneously in something like a high-speed power plant turbine? Keep that physical, real-world machinery moving in your mind as you study. Finish up your tutorial sheets, practice these calculations until they are second nature, and good luck on those final exams.